Hello, my name is Diogo Barradas from INESC-ID, Instituto Superior Técnico, Universidade de Lisboa. Today I'm going to talk about FlowLens, a system that leverages programmable switches for enabling efficient traffic analysis in large-scale networks. As of today, there have been a number of performance breakthroughs in large-scale networks enabled by programmable switches. These kind of devices are able to process packets at line speed and are fully programmable with a P4 language. They have also been the recent focus of hardware manufacturers, and this is interesting because they actually bring new opportunities in the network security realm. As a matter of fact, different authors have actually used programmable switches to obfuscate network topologies, to filter spoofed IP traffic, to mitigate DDoS attacks, and also to thwart network covered channels. By leveraging the opportunities of programmable switches to actually process packets at line speed, all these approaches are highly efficient. However, they are also fine-tuned for specific application domains. In particular, previous approaches actually ignore a number of machine learning-based security applications, such as the detection of botnets, website fingerprinting, which holds on the identification of a particular website browsed over an encrypted tunnel, the analysis of the behavior of IoT devices, and also the detection of network covered channels. One thing that all these applications have in common is their reliance on statistical traffic analysis and on the inspection of the distribution of packet lengths or packet inter-arrival times of different flows tied with the use of a machine learning-based classifier. Statistical traffic analysis techniques are also general in the sense that they act as a generic approach towards detecting multiple attacks. However, collecting packet distributions in programmable switches is actually a hard task, and this is mainly due to two reasons. The first reason is that stateful memory within this kind of devices is actually severely limited and amounts just to a few hundreds of megabytes. In a nutshell, this means that we just have no memory for storing the packet distributions of many flows that can cross the switch concurrently. On the other hand, we know that packets must be processed at line speed, which means that we just have a limited number of operations that can be performed per packet while using a reduced instruction set provided by the device itself. So discuss the question of whether it is feasible to actually obtain these packet distributions in programmable switches and do this at scale. So our research question is whether we can actually collect these packet distributions within programmable switches in such a way that this collection can be performed in an efficient fashion and in a generic way to support multiple machine learning-based applications. Unfortunately, it is known that some solutions for collecting packet distributions in programmable switches do have a few drawbacks. For instance, packet aggregation approaches like StarFlow duplicate packet headers or specific fields to a monitoring server. Albeit being generic, these approaches actually incur in a large bandwidth cost while duplicating packets to the monitoring server. On the other hand, we have approaches like NetWarden, which can efficiently inspect packet distributions within programmable switches, but are very application tailored. In our paper, we introduced FlowLens, a flow classification system for generic machine learning-based security applications. With FlowLens, we deliver two main contributions. Our first contribution is the generation of flow markers, which are a compact representation of packet distributions within programmable switches. We also implement the flow marker accumulator in switching hardware, which allows us to collect these flow markers within the programmable switch. Our second major contribution is an automatic profiling process, which can actually tailor the composition of these flow markers in an application-specific way. Finally, we tested FlowLens in 3 different security tasks, and we are actually able to confirm that FlowLens is both efficient and generic to support a multitude of machine learning-based applications. This figure shows FlowLens architecture. When a client wants to use FlowLens, it can upload a training dataset for a particular machine learning-based task to our profiler server. Our profiler server will then use supervised machine learning to select the correct composition of the flow marker that better suits that kind of machine learning application. These parameters will then be uploaded to a P4 program that is running on the switch, and that will actually collect and compress packet distributions as new flows cross the switch. Periodically, these flow markers will be collected by the CPU of the switch, which will also perform the classification of network flows. Once these results are done, these are actually propagated back to the client. It is worth noticing that FlowLens also supports distributed deployment, which enables us to scale the number of measured flows and ensure network visibility in the case of switch downtime. And FlowLens also supports a coordinated operation, such that multiple machine learning applications can be run in different places of the network. So, to compress packet distributions efficiently, FlowLens actually makes use of 2 operators, quantization and truncation. So in this plot we can see what raw packet size distribution for a particular flow looks like if we assume the maximum packet size to be up to 1500 bytes. By using quantization, what we will obtain is a coarser representation of this same distribution. Further, by applying a pre-training step using a supervised learning algorithm, we can actually select which are the top n most important bins from this quantized distribution and use that as our flow marker. By following this process, we can actually see that we are able to compress the original packet size distribution over 150 times. Since there is a large space of quantization and truncation parameters, we leverage Bayesian optimization to build an automatic profiler. This automatic profiler can help us selecting the best flow marker for a particular kind of machine learning application. In fact, this automatic profiler can work with 3 different criteria and can give us the smaller marker for a target accuracy. It can give us a flow marker that provides the best accuracy given a size constraint, and also can automatically find a compromise between a marker size and the accuracy. And so this actually saves us many hours of testing what could be suboptimal configurations. Before showing you how flow markers are collected into the switch, I'm first going to guide you through how the architecture of a programmable switch looks like. These switches are composed by a programmable packet parsing pipeline that leverages match action tables arranged into a number of stages. Each of these tables can match some packet field and trigger an action that can change packet headers or metadata tied to that packet. So we actually use programmable switches for implementing our flow marker accumulator, whose stages are mapped into the packet parsing pipeline as shown in the figure below. Stage 1 will be responsible for performing the quantization operator, and stage 2 will be responsible for performing truncation. The remaining stages will be used to match flows to their corresponding flow markers in the register grids located in memory clusters. So what happens when a new flow actually reaches the switch? Suppose that we have a new flow ID reaching the switch. This flow will be communicated to the control plane, and the control plane will actually index this flow in the flow table of the data plane. It will also set a flow offset in the register grid so that we know which is a particular location of this grid where the flow marker for that particular flow is located. So now what happens to the packet size of this flow? Well, in stage 1, this packet size will be quantized and we will obtain the bin index 16. In stage 2, we must check whether this bin should actually be accounted for. Since the truncation flag is set to 1, we should be accounting this quantized bin, and since the bin offset is equal to 1, we also know that this is the second bin that is being part of the flow marker for that particular flow. In stage 3, nothing will happen because the flow is not indexed in this table, but the flow is actually going to match in stage 4. When this happens, we'll compute the cell offset, which is given by the sum of the flow offset computed previously by the control plane and the bin offset previously computed in stage 2, and we'll actually obtain 11, which is the position in the register grid where we should increment the bin. Finally, in stage 5, we'll perform the incrementation of the correct position of the flow marker. By doing this, we can actually compress packet distributions at line speed. We evaluated FlowLens in 3 different dimensions. First, we evaluated the scalability of our system in 3 different use cases, including the detection of cover channels, website fingerprinting, and botnet detection. We also tested the performance of the FlowLens profiler and assessed the resource consumption that FlowLens incurs both in the control plane, respectively the CPU usage, and in the data plane of the switch, the ASIC usage. This table shows us the scalability gains of FlowLens in 3 different use cases. For instance, we can see that in cover channel detection, we are able to scale the measurement of flows to over 150 times, while losing only 3% in the accuracy of these machine learning based tasks. Similarly, for website fingerprinting, we can scale the number of flows over 30 times and just lose 2% in the accuracy of this machine learning based task. In the interest of time in this presentation, I'm just going to detail how we actually reach this scaling for the cover channel detection use case, but I invite you to check our paper for a more comprehensive evaluation. This plot shows how the accuracy of the cover channel detection task is actually impacted as we increase the quantization level when generating flow markers. In this table, we can also see that the higher quantization level that we have, the less memory it is needed to actually represent the packet distribution for a particular flow. Further, we can see that for detecting cover channels while using raw packet size distribution, we will use a flow marker of a size of 3000 bytes, and we will be able to detect cover channels with a 96% accuracy. We can also see that, for instance, using quantization level 4, we could shrink the size of this packet size distribution from 3000 bytes to just 188 bytes and still achieve a detection rate of about 92% accuracy. And in a nutshell, this actually means that we can have an increase of 16 times in the number of measured flows in the switch. Additionally, we can further apply truncation and check that, for instance, by selecting just the top 10 most important features of the quantized distribution, we can actually shrink the packet size distribution from 3000 bytes to just 20 bytes in the size of the flow marker and still achieve a detection rate of about 93% accuracy, which is just 3% less than detection with full information, and you can actually scale the number of measured flows by 150 times. We can also see that FlowLens is able to achieve good quantization and truncation parameters. For instance, in the covered channel use case, we had 48 valid parameter configurations. By using our automatic profiler and setting a maximum exploration of 10 combinations, we actually obtained the results below. We can see that our profiler is able to optimize for reasonable size and accuracy trade-off of the flow marker, outputting a combination that has a flow marker of just 20 bytes size and achieves an accuracy of 0.944, while for instance other combinations explored by the profiler could actually achieve a better accuracy, such as the first one would achieve 0.96 accuracy, but which would also use a much larger flow marker. It is also worth noticing that FlowLens imposes a small overhead in the resources of the switch. Consider for instance the CPU usage. When using the botnet detection model, which was our largest model, we'll just use 140 megabytes out of 32 gigabytes of RAM available in the device, and we'll just use 5 megabytes of storage. Additionally, we'll just spend 200 microseconds per prediction. This, in a nutshell, also means that FlowLens is actually able to support flow classification in the control plane of the switch. Regarding the ASIC usage for implementing the flow marker accumulator in the data plane, we can see that FlowLens leverages minimal computational resources, and while it uses some SRAM for storing flow markers, it doesn't actually use TCAM at all. This also means that actually FlowLens supports the concurrent execution of other forwarding behaviors in parallel. Before closing my presentation, I would like you to keep in mind a few remarks. FlowLens is the first traffic analysis system for generic machine learning-based security applications in programmable switches, and it is able to collect compressed packet distributions while ensuring classification accuracy and a small memory footprint. It is also able to classify flows directly on the switch, saving important communication, compute, and storage costs. Please check our code, which is available on GitHub, and thank you. I'll be available for answering any questions.